Okay, we left with this nice picture. Uh, this is a bit too long. With this nice picture of uh, this exponential form of the complex number that basically flips from 1 to -1. Uh, okay, and from I to -I, depending on the power of the exponent. If it's so, if I to the x to the 2n is equal to -n x to the 2n when it's even, and when it's odd, you get -n I x to the 2n plus 1. Okay, and fine, we have these two group of symbols that compose e to the ix, which is roughly equal to the sum up to n from 0 to, so the first function, where are the even component, plus a second function where n, where are the, and there is an I, where are the odd component. Okay, factorial. We call this f of x, and we call this g of x. Okay, the idea is that eventually, when we saw this already in the unit circle, when we have a complex number with the radius 1, so modulus z equal to 1, the real part and the imaginary part are also the, and this is x, are also the cosinus of x and the sinus of x. This is just by a simple trigonometry of the triangle here. But we want to be a bit more specific, and we want to see that this function here that I'm computing with the sum up to n can become effectively the cosinus of x and the sinus of x when n tends to infinity, when n is large. But I'm not going to do the limit to infinity. I'm going just to prove some facts about these two functions, and to try to convince you that are rightly called sinus and cosinus. Okay, so we start with the fact that f of 0 is 1 and g of 0 is 0. And this is true because if we lock the function to the first bits, okay, and we plug 0 in x, this goes away, this goes away, this goes away, and we are left with 1. So f of 0 is 1. If we do the same with the g of x, which is the odd power series, basically 5 and then 7 factorial, and then we place x equal to 0, we get all zeros, so we get g equal to 0. And this is reassuring starting point, because if you remember the plot of sinus and cosinus, we get the sinus is like this, and the cosinus is like this, and the starting point is exactly 1 and 0, as we expect. Okay, now but this is not enough to prove that our two sum are the cosinus and the sinus. We want to give a little bit more, so we want to show, for example, another properties that shares this function, which is f of x is equal to f of x, which is true because if you have 1 minus x squared plus, okay, I will stop to the third term, it doesn't matter, and we replace x with minus x, okay, they get the same. They get the same value because minus elevated um, to the even power is cancelled, so we get the same function. So, and this is, by the way, it's also true for the cosinus, which is an even function, okay, and which means that whatever it's in this half is the same as this half, exactly the same. And then we can show that f of minus x, g of minus x, sorry, g of minus x is equal of minus g of x. And this is because x minus x cubed, for example, plus x to the fifth power over 5, if we replace x with minus x, we switch the signs because minus to the odd power is always minus. Okay, so, and in fact we know that sinus is antisymmetric. Whatever it's here is 1, for example, this is flipped to minus 1, and all the points are so on. So, okay, these are nice properties, but we are not quite sure that we are dealing with the correct approximation of the function, at least. So let's see if we can do a little bit more. So far so good, but I want to do a step forward, which is basically proving this nice relation between these functions, which tells us a great deal about them. And by the way, there is also the same relation with the plus and the minus. How do we do that? Okay, so we take f of x and we sum the first 3 bits of it, and we should prove it then for all of them, but I'm not going to do it. Just maybe leave you to think about how to do it, but basically the trick is the same. It's just a bit lengthy to work out all the details. So the first step are these ones, and the first 3 steps are these ones, and okay, and to compute these values, we go here and we just remember this nice fact that a plus b to the n can decompose in many terms, and the coefficients of the terms are placed such that these numbers are used basically. And you can get this number. This is order 0, order 1, order 2, order 3, order 4, which is the exponent here. And you can get this number by summing the one above. And as you can see, this sum works out nicely. So let's see how it works with the 2 terms that we have. This is x squared minus y squared minus twice x divided by 2. And this 2 here is exactly this one in the middle because it's order number 2. Okay, then we do the same for order number 4, and no surprise, we follow the same rule, and then we get some extra, so this coefficient here, the 4 factorial plus 6x squared y squared divided by 4 factorial. Okay, so far so good. We've got this term. We should have many dot 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 dot, we know that, but at the moment we are happy with the few bits to begin with. And now we do the other part of the equation, and let's see if it gets the same result. Okay, so let's do f of x times f of y minus g of x, g of y, and this is easily done. 1 minus x squared plus x4 4 factorial times 1 minus y squared divided by 2 plus y4 4 factorial minus x cubed, and I will stop to the second term because already the degree is high enough to match the one on the row below. So to match this value here. So we want to replicate these numbers. Okay, let's see if we can do that. Okay, and this is equal to 1, I guess, from this times this, and then we get minus x squared times 2 minus y squared times 2, and then we have the double product, which is square divided by 4, and then we get plus y4 divided by 4 factorial, x4 divided by 4 factorial, that's fine, and then we get many terms with higher exponents, we don't care, and then we get this minus xy term here, and then we get plus x cubed divided by 3 factorial and plus xy cubed divided by 3 factorial. Okay, so, and all the other terms are higher than the fourth power, so we don't care, we stop at the fourth power and compute if they are all the same. And apparently they are, because we can check. 1 is here, x squared and y squared are here with the correct sign, x to the power of 4 and y to the power of 4 are here with the correct sign, and then minus xy it's there, minus xy, and then we've got these other terms which looks different, but if we look carefully each of them, we have xy divided by 4, which can become, if we multiply by 3 factorial over and down, which doesn't change the value, become xy squared divided by 4 factorial, which is exactly this number here, which is fine. And also we got terms like xy cube 3 factorial, and if we multiply, actually this is a 4, if we multiply them by 4 and divide it by 4 in the same amount, because otherwise we are changing the number, we get exactly this number here down there, and so on. Okay, so what I'm saying is that we can do this bit by bit, order by order, and we will, with no surprise, or maybe actually with lots of surprise, because this is a characteristic that not every function has, we can see that this formula up here is correct. Okay, and it works as well with the sign, with the other sign. This is good. Let's see what we can do with this formula. And by the way, if we use the other function to start with, g of x plus or minus y, we can show, not going to do it, but that this other relationship holds. Okay, fine. At the moment we just need the first one. Why we need the first one? Because we want to do the following. We calculate f of pi plus 0, and I will tell you in a sec why I'm explicitly write the 0, because I want to use let me erase this one because we don't need, I won't use it, but by the same logic we can get the result. Let me write explicitly the one that I'm going to use, which is this one, okay, with a plus and g of y, and this is a plus. Fantastic. Okay, so now you see where I'm going with this. F of pi plus x, pi minus x, which is 0, which is equal actually minus 2 times g of pi times g of pi. Okay, and this tells us that f of pi minus f of pi, which is 0, is equal to minus 2 times g pi. square, meaning that g pi square is equal to 0, because this is 0, and the only way to make a square 0 is to have the argument equal to 0, which is good because the function g in 0 is 0, but also in pi is 0, the same way as sinus pi is 0, so which is good. Let's see if we can get other numbers out of it. I'm sure we can. We can get, for example, 2 pi. So we just replace the 0 with a pi and a pi here. Okay, and this is actually f of 2 pi. Sorry, let me do it correct. F of 2 pi minus 1 is equal, yes, is equal to minus 2 g of pi square. Okay, so f of 2 pi, but we know that g of pi is 0, so this side is 0, so f of 2 pi plus 1 is equal to 1, which is true because the function f, which should look like the cosinus, in 2 pi, which is down here, is exactly the same point as here, which is 1. And in fact is periodic by that much. And let's see if we can get another number just to keep filling the gaps and making sure that we are using the correct function here. So if we use divided by 2, okay, this is divided by 2, this is divided by 2, divided by 2, divided by 2, pi over 2, it means that f of pi minus f of 0, which is 1, is equal to minus 2 g pi squared. But now we know that f of pi is 0, so we have that 1 is equal to 2 g pi half squared. Sorry, f of pi is not 0. F of pi, g of pi is 0. F of pi we need to find it, or what it is, f of pi, which we cannot do by using this. We would use the other formula. Okay, yes, sorry, this is me going nuts. F of pi, we need to use the other formula, which I didn't use. But anyway, so let me see if I can do that bit, which would be nice, which was basically g of x plus y and g of x minus y. We get f of x, f of y plus, sorry, g of y plus f of y, g of x, and then we get f of x, g of y minus f of y, g of x. And the role is changed, so we now do g, let's see what we get with g pi plus 0 minus g pi minus 0. Okay, here we get minus 2 times f of pi, sorry, g of pi. Okay, f of pi, g of pi, this is a g. Let's see if we can get this done. So g of pi and g of pi is 0. So we get that, and we know that f of pi is 0, so we don't get much out of this equation. Let's see if we can get, so this is not very useful, countable are not useful. Let's see if I can get this one, 2 pi, g of 2 pi. And this should be done, this should be good, f of pi, g of pi. Let's see if it's this works out. So g of 2 pi and g of 0, which is 0, it's equal to, we know that g of pi is 0, which is 0, and we know that basically we get that sinus of 2 pi is equal to 0 as well, which is okay, but we want to get something out of f. So let's see if I can get this right. We want to do, for example, f of pi. So let's see if I can get this with the g of pi over 2 plus pi over 2, and this is minus g of 0, because it's the difference, minus 2 f of pi over 2 g pi over 2. Okay, now this is g of pi, g of 0 is 0, f of pi half we don't have, and g of pi half we don't have. But we know that g pi is 0, so this is 0 as well, so we get that 0 is equal to f of pi times g of pi. So one of these two numbers is 0. Okay, it cannot be g of pi half, so it's actually f divided by pi divided by 2, and this is equal to yes, this is equal to 0, and which is this point here, pi over 2. And if we do now the other components, basically if we get the other components, we would see that instead g of pi over 2 is equal to 1. Now we note it down here, g of pi over 2. We can find that is equal to 1, which is correctly so, as in this graph. Okay, and then we can get all the other numbers by following these rules repeatedly. Okay, just to recap, these are let's say relations that works for the cosinus and the sinus, and the sinus as well. So when we sum all the bits up to infinity, we will get this exact relationship, and we are happy that we know that we are creating this function. But so far we are just limiting to this simple understanding. Okay, then what I want to do in the next video is to finish off by basically telling you how to do the exponential of a matrix finally. But I needed all this stuff to do the math right, otherwise it's a bit dodgy. Okay, so follow me for the next one then.